Content repository in Apache NiFi. Now we are focusing on content repository. The content repository is where the actual content bytes of a given flow file live. The implementation of the repository is pluggable. The default approach is a fairly simple mechanism which stores blocks of data in the flow system. More than one file system storage location can be specified so as to get different physical partitions engaged to reduce contention on any single volume. Here you can see a copy on write. In this example, we are focusing on the compress content processor of the template that compresses bundle of merged flow files containing web pages that were queued. In this example, the content C1 for flow file F1 is being compressed in the compress content processor. Since C1 is immutable and we want a full replayable provenance history, we can't just overwrite C1. In order to modify C1, we do a copy on write, which we accomplish by modifying the content as it is copied to a new location within the content repository. When doing so, the flow file F1 is updated to point to a new content C2, and a new provenance event P2 is created, referring to a new flow file F1.1. Because flow file repo is immutable, instead of modifying old F1, the new delta F1.1 is created. Previous provenance events still have the pointer to the C1 to the content C1 and contain all attributes, but they are not the most up-to-date version of the flow file. For the sake of focusing on copy on write event, the flow file F1 flow file F1's provenance events leading up to this point are omitted here. Here you can see before success is connected to compress content, and it's interact with success, and F1 is pointing to C1 in flow file, and in content you can see C1. In after success is connected to compress content, and it's interact with success, and in flow file repository you can see the F1 is pointed to C1 is there, and now new one new 1.1 is pointing to C2, and in the content repository, this C1 is the plain text, and here C2 is compressed, and in provenance here C2 is pointing to F1.1. it's in the modify. Here you can see copy on write in NiFi. The original content is still present in the repository after flow. In this example, consider a processor that compresses the content of the flow file. The original contents remains in the content repository, and a new entry is created for compressed content. The content repository finally returns a reference to the compressed content. And the flow file is updated to point to the compressed data. This drawing sums up the example with the processor that compresses content of flow file. Here you can see processor is connected to content repository, and in content repository original content is connected to compressed content is moved to content original content is connected to compressed content on copy on write here, and compressed content is connected to process. Here you can see that content repository has 35% of its disk consumed by content claims that are tied to flow files still active somewhere in one or more data flows on the NiFi canvas. This leaves 15% of the disk space to be used for archived content claims. There are three properties in the NiFi.properties file that deal with archiving on content in the NiFi content repository. The default NiFi values are NiFi.content.repository.archive.max.retention.period equal 12 hours. NiFi.content.repository.archive.max.usage.percentage 50%. NiFi.content.repository.archive.enabled equal true. Purpose of content archiving is so that users can view and or replay content via the provenance UI that is no longer in the data flows. The configured values do not have any impact on the amount provenance history that is retained. If the content associated to a particular provenance event no longer exists in the content archive, provenance will simply report to the user that content is not available. The content archive is kept within the same directory or directories where you have configured your content repositories to exist. When a content claim is archived, that claim is moved into an archive subdirectory within the same disk partition where it originally existed. This keeps archiving from affecting NiFi's content repository performance with unnecessary writes that would be associated with moving archived files to a new disk partition, for example. The configured max retention period tells NiFi how long to keep archived content claim before purging it from the content archive directory. The configured max usage percentage tells NiFi at what point it should start purging archived content claims to keep the overall disk usage at or below the configured percentage. This is a soft limit. Let's say the content repository is at 49% usage. The 4 GB content claim then becomes eligible for archiving. Once at time this content claim is archived, the usage may exceed the configured 50% threshold. At the next checkpoint, NiFi will remove the oldest archived content claims to bring the overall disk usage back or below 50%. So this value should never be set to 100%. These two properties are enforced using an or policy. Whichever max occurred first will trigger the purging of archive. Here you can see the content repository, and disk free space is 50% and archived content claims 15%, active content claims 35%. As an example, we can consider content repository interface. Defines the capabilities of a content repository. Append options are not available on the methods, but a merge capability is provided, which between that and creating new claims, a merge. As an example, we can consider IO exception as an example for an exception. This occurs if unable to init in initialize method in interface content. As an example too, we can consider property NiFi.content.repository.directory.default strict. The location of the content repository. The default value is ./content_repository. Multiple content repositories can be specified by using the NiFi.content.repository.directory prefix with unique suffixes and separate paths as values. For example, to provide 2 additional locations to act as part of the content repository, a user could also specify additional properties with keys of NiFi.content.repository.directory.content1 equal /repos/content1, NiFi.content.repository.directory.content2 equal /repos/content2. Providing 3 total locations, including NiFi.content.repository.directory.default. This property is available in NiFi. Here you can we are considering replaying a flow file in data provenance. In the content tab shows information about flow files content, such as its location in the content repository and its size. Now we are considering content repository in system properties. The property NiFi.content.repository.implementation. The content repository implementation, the default value is Apache.NiFi.control.repository.filesystem repository. The content repository holds the content for all flow files in the system. By default, it is installed in the same root installation directory as all of the other repositories. However, the administrator will want to configure it in a separate drive if available. If nothing else, it is best if the content repository is not in the same drive as the flow file repository. In data flows that handle a large amount of data, the content repository could fill up disk, and the flow file repository, if also on that disk, could become corrupt. To avoid this situation, configure these repositories in different drives. That's a kind of guideline for configuration. Now here we are considering the property basically NiFi.content.repository implementation. Now we are considering content repository. The condition the condition for archiving and or deleting are configured in the NiFi dot properties file. The content repository is simply a place in local storage where the content of the flow files exist, and it's typically the largest of the three repositories. As this repository utilizes the immutability and copy on write paradigms to maximize the speed and thread safety. The core design decision influencing the content repo is to hold the flow file content on disk and only read it into JVM memory when it is needed. This allows NiFi to handle tiny and massive sized objects without requiring producer consumer processes to hold the full object in the memory. As a result, the actions like splitting, aggregating, and transforming very large objects are quite easy to do without harming memory. In the same way, the JVM heaps has a garbage collection process to reclaim unreachable object when space is needed. There exists a dedicated thread in NiFi to analyze the content repo for unused content. After a flow file content is identified as no longer in use, it will either be deleted or archived. If archiving is enabled in the NiFi.properties, then the flow file's content will exist in the content repo either until it is aged off, deleted after a certain period amount of time, or deleted due to content repo asking too much space. The conditions for archiving or deleting are configured in the NiFi.properties file. NiFi.content.repo.archive.max.retention.period or archive. Or NiFi.content.repository.archive.max.usage.percentage, and outline in the NiFi system at administrator guide. Now we are considering content claim in deeper view in content repository. To keep track of the flow file's contents, the flow file has a content claim object. In general, when talking about the flow file, the reference to its content is simply be referred as the pointer to the content. Though the underlying implementation of the flow file content reference has multiple layers of complexity. The content repository is made of a collection of files on disk. These files are binned into containers and sections. The section is a subdirectory of a container. Container can be thought of as a root directory for content repository. The content repository, though, can be made up of many containers. This is done so the NiFi can take advantage of multiple physical partitions in parallel. NiFi is then capable of reading from and writing to all of these disks in parallel. In order to achieve the data rates of hundreds of megabytes or even gigabytes per second of disk throughput on a single node, resource claims are Java objects that point to specific files on disk. This is done by keeping track of the file ID, the section of the file in it, and the container in the section is the part of. To keep track of the flow file contents, the flow file has a content claim object. This content claim has a reference to the resource claim that contains the content. Offset of the content within the file and the length of the content. To access the content repository drill down using the specific file on disk using resource claims properties, and then seek the offset specified by the resource claim before streaming content from the file. This layer of abstraction resource claim was done so that there is not a file on disk or content of the every flow file. Concept of the immutability is the key to this being possible. Since the content is never changed once it is written, copy on write is used to make changes. There is no fragmentation of memory or moving data in the content of a flow file changes. By utilizing single file on a disk to hold content of the many flow files, NiFi is able to provide far better throughput, often approaching maximum data rates provided by the disks. As an error example, we can consider this one. Nothing is archived directory in content repository. This occurred in archive. Now this is the end of my presentation. Thank you very much for watching it.